Hey Math 135, what's up? In this video we're going to be looking at some extra examples in section 8.6 on applications of the normal distribution. If you're not very confident in your ability to work with the problems in 8.5, you should go back and work on those problems because we're going to be going through some of those ideas rather quickly in this video. So if you find yourself not quite understanding what we're doing, then you might benefit from going back and looking at 8.5 where we introduce the normal distribution. In number 1, it says on average a student takes dictation at a speed of 100 words per minute midway through an advanced court reporting course at the American Institute of Court Reporting. Assuming that the dictation speeds of students are normally distributed and that the standard deviation is 30 words per minute, what is the probability that a student randomly selected from the course can take dictation at a speed in part A of more than 170 words per minute? So in this problem in 1, we're talking about a normal random variable x. X is a normal random variable. It says on average, x would be the dictation speed, words per minute. X is measuring words per minute, and it's a normal random variable with a mean of 100 words per minute and a standard deviation of 30. And in part A, there we're trying to find the probability that a student's words per minute, their dictation speed, is more than 170. Right, so we have a normal random variable. We need to standardize this normal random variable, use a z-score. So the z-score here, remember z is x minus mu over sigma. In this case, that will be 170 minus 100 over 30. And that gives us a z-score of about 2.33. We're going to round all of our z-scores to 2 decimal places, just as they are on our z-table. Okay, so when we standardize this normal random variable, that gives us the probability that a standard normal random variable z is more than this z-score, 2.33. All right, now we have a more than problem about a standard normal random variable z. We want to use our z-table, but our z-table only gives us the less than answers, so we have to convert this to a less than. We have two options. We can use the complement and say that this is the same as 1 minus the probability that z is less than 2.33. Or we can use symmetry to say that this is the same as the probability that z is less than negative 2.33. Again, those ideas are discussed in the section 8.5 supplement video. All right, so I'm going to go ahead and go with the bottom version. We got to find our z-table here and look up negative 2.33. All right, so there's our z-table. We want the negative 2.3 row over to the 0.03 column. All right, we got some 0.0099, and that's our answer. All right, in part B, we want to know the probability that the student's dictation speed is less than 20 words per minute. So we are once again going to need to standardize this normal random variable with a z-score. In this case, the z-score will be 20. That's the x value minus the mean of 100 divided by the standard deviation of 30. And that will give you a z-score here of negative 2.67. So when we standardize this normal random variable, that gives us the probability that a standard normal random variable z is less than that z-score of 2.67. So we do have a less than problem with our z-score. We can go ahead and go straight to the z-table for this one. No need for any fanciness. We're looking for negative 2.67. Got the negative 2.6 row over to the 0.07 column. That gives us 0.0038. Okay, so for the purpose of getting through these problems in the video, I'm going to go ahead and skip the part where I look at the z-table every 2 seconds. So again, we're gonna go ahead and assume from this point that you know how to use your z-table. If you need help with the z-table, go back and watch that 8.5 video. All right, then in part C, we want to know the probability that the dictation speed is between 20 and 170. So that's our dictation speed is our normal random variable x. We want that to be between 20 and 170. So we need 2 z-scores. We've actually already computed both of those z-scores. When we standardize this problem, that's going to be the probability that our standard normal random variable z is between, let's see, the z-score for 20 was negative 2.67, and the z-score for 170 was 2.33. So here we have an in-between problem with our standard normal random variable z. Strategy here is we split that into 2 less than problems. The probability that z is less than 2.33, the larger number, minus the probability that z is less than the smaller number, 2.67. All right, if we find the corresponding probability for the z-score of 2.33 in the table, that will be 0.9901. And then we've already looked up the probability for the second one. That was part B, 0.0038. And after the subtraction problem, we end up with the final answer of 0.9863. Please take time if you need to make sure that you can use your z-table to find these values and that you can use your calculator to do the computations. Moving on to number 2. The tread lives of Super Titan radial tires under normal driving conditions are normally distributed with a mean of 40,000 miles and a standard deviation of 20,000 miles. So we're going to have a random variable x, which is going to give us the tread life. And the problem tells us that it's a normal random variable with a mean of 40,000 and a standard deviation of 2,000. And in part A, we're looking for the probability that a tire selected at random will have a tread life of more than 35,000 miles. So the probability that our tread life, that's our random variable, is more than 35,000. Okay, so we have, again, another normal random variable problem. We need to standardize it with a z-score. Here the z-score would be our x value, 35,000, minus our mean of 40,000, divided by our standard deviation of 2,000. And that would give us a z-score of negative 2.5. So when we standardize this normal random variable, we get the probability that a standard normal random variable takes on a value greater than negative 2.5. So that's a greater than problem. Again, there's two strategies that work here. I'm just going to go ahead and use the symmetry strategy to say that this is going to be the same as the probability that z is less than positive 2.5. Again, the symmetry strategy says flip the inequality and flip the sign of your z-score. And then the probability that corresponds to a z-score of 2.5 in the table is 0.9938. And we can be done there. Okay, part B, determine the probability that 4 tires selected at random still have useful tread lives after 35,000 miles of driving. Assume that the tread lives of the tires are independent of each other. So this is a little bit of a trick question here. Kind of shows up out of the blue. We actually have a different random variable going on here. I guess this is one way to deal with the problem. Is we have a new random variable y that's going to be the number of good tires after 35,000 miles. It is a binomial random variable. Let's talk about that for a second. We have a fixed number of trials. There's 4 tires. And in each trial, there's a success and failure. The tire is successful if it's still good, and it's a failure if it's bad. And the probability that it's still good, that was the thing that we found in part A. The probability that the tire is still good is 0.9938. And the probability that our tire fails, the Q value here, would be 0.0062. And the question here is asking, what's the probability that the number of good tires after 35,000 miles is 4 out of 4. Since this is a binomial random variable, we can use our binomial formula to compute this probability. And that would be, let's see, we have a y, I guess a little y of 4. So here, I guess, the binomial formula would look like the probability that y is equal to little y is n choose y times p to the y times q to the n minus y. So we're just using y instead of x, because we already used x for the normal random variable in the bigger problem. So here we've got 4 choose 4 times p to the 4, that's 0.9938 to the 4, times q to the n minus 4, which would be 0. And if you worked it on your calculator, you should get an answer of about 0.9754. So between a 97 and 98% chance that all of these tires are still going to be good after 35,000 miles. Now that's one way to deal with the problem. You can treat it like a binomial random variable. You could also just kind of simplify this a little bit. We didn't necessarily talk about anything like this in class really, but you could simplify it and say, since they're independent, most of our independent problems we just had like two trials, but here we've got like 4 trials of independence. And so you could, think about, a 4-stage good or bad. The first tire is good or bad, and the second tire is good or bad in each case, and build this tree. And the idea is we just want all 4 tires to be good. And there's only one path down this tree where everything's good. And so you could take, I guess, and since the tires are independent, the probabilities are always this p-value, 0.9754. So you could all of the probabilities down this tree would be p. And so you could get that this is 0.9754. Where did I get 0.9754? It's 0.9938. Sorry about that. 0.9938. That's our probability that our tire is good. Okay. And so you could do 0.9938 to the fourth when you multiply down that tree. And that would also give you 0.9754. That's because 4 choose 4 is just 1, and 0.0062 to the 0 is also 1. So that's another way to deal with this particular binomial random variable. When you have all successes or no successes, you're just taking the appropriate probability and raising it to the full power. All right, moving on to number 3. General Manager of the Service Department of MCA Television has estimated that the time that elapses between the dates of purchase and the dates on which a 50-inch LCD TVs manufactured by the companies first require service, yikes, that's a mouthful. This time that elapses is normally distributed with a mean of 22 months and a standard deviation of 4 months. If the company gives a 1-year warranty on parts and labor for these TVs, determine the percentage of the TVs manufactured and sold by the company that will require service before the warranty period runs out. Holy smokes, that is a mouthful of a problem there. So the idea here is that we have the thing that's normally distributed is the time that elapses between the dates of purchase and the dates where they require service. That's our random variable. All right, so I guess we could say that this is time to crap out for this TV. And it's a normal random variable with a mean of 22 months and a standard deviation of 4. Now the warranty is 12 months, and the problem is here. The problem is asking for the basically. The problem is asking for the percentage of TVs. So we can interpret it as the probability that a TV will crap out before the warranty, before 12 months. So what's the probability that the time it takes to crap out is less than 12 months? Okay, there we go. I think that was the biggest challenge here is, sifting through all those words to write down a probability problem about a normal random variable. But now that we've got it, we can go ahead and do it. We have to standardize this normal random variable. Our z-score here will be 12 minus 22 all over 4. That'll give us a z-score of negative 2.5. And so this is the same as the probability that our standard normal random variable z is less than negative 2.5. And if you go look up that value on the z table, that'll give you 0.0062. So yeah, once I think reading the story here and determining what we want, I think from a test taking or math 135 meta perspective, we're looking at a normal random variable here, and we can assume that our probability. Oops, I almost forgot. They didn't ask us for the probability. They want a percentage. So we could say 0.62% or less than 1%, which I suppose is good. 1% of TVs. Anyways, understanding that we're trying to find a probability about a normal random variable, then it's not as big of a leap to understand that this is the probability that we're thinking about. On to number 4. The mean IQ score is 100 with a standard deviation of 15. Now that's true. That's how the IQ test is designed. If they find out that the mean IQ is not 100 and the standard deviation is not 15, they rescore things. So anyways, part A, what IQ score represents the lower 10% of the population? And they're telling us here to round our IQ scores to the nearest whole number. So this is a backwards problem. They gave us basically a probability. We're talking about a lower 10%, so that's a good probability to be working with. And they're asking us to find an IQ score. So there is some IQ score X. I guess we have a normal random variable X, which is the IQ score. Again, the problem tells us that it's normally distributed with a mean of 100 and a standard deviation of 15. And there is some IQ score, little x, where the probability that a score is less than that is 10%, or 0.10. They're asking us to find out what that score is. Okay. So this IQ score, this unknown IQ score x, there's a corresponding z-score that we don't know yet. That would be x minus mu over sigma. And the corresponding probability for that z-score would also be 0.10. So I guess I will go ahead and bust out my z-table again. We're trying to find this is a probability. We're trying to find 0.10 on the inside of the z-table. Let's see. I feel like I'm getting close. Maybe not so much. There we go. Okay. Between these two values here, 0.1003 and 0.0985, the one that's closer is 0.1003. That corresponds to a z-score. We're in the negative 1.2 row and in the 0.08 column. So that corresponds to a z-score of negative 1.28. All right, so we got our z-score now. Negative 1.28. And then we can go ahead and use that along with our z-score formula to solve for x. We got negative 1.28 is equal to x minus 100 over 15. And then you can solve for x. We multiply by 15 on both sides. Negative 1.28 times 15 is x minus 100. And then add 100 to both sides to get x is negative 1.28 times 15 plus 100, which will give you an IQ score of 80.8, which, remember, we got to round to the nearest whole number. That would be an IQ score of 81. All right, so 81 would be kind of the cutoff point for the lower 10%. If you get an IQ score of less than 81, then you're in the bottom 10% of the population. In Part B, Mensa International, which is an organization for those with high IQ scores, only accepts those in the top 2%. What is the minimum IQ score needed to become a member of Mensa? So this is a similar problem. There's some score little x, where if your IQ is more than that value, then you are in the top 2%. So the probability that you score higher than that value is 2%, or 0.02. Now we can't work with these greater than problems all that well, so we could say that the probability that an IQ score is smaller than that value is 98%, or that 98% of the population scores less than that value. And it's much easier to work with the less than problems. All right, there's a corresponding z-score, where the probability that our standard normal random variable takes on a value less than z is also 0.98. We want to find that z-score in the z-table, and so we will look for a probability. Since it's bigger than a half, we want to go over to the positive side. Find the number closest to 0.98. I think here we are right here, between 0.9798 and 0.9803. I think 9798 is just a little bit closer, so we're working with a z-score of 2.05. 2.05 is the z-score that we're working with. And so again, we will use that z-score along with the z-score formula. The z-score would be equal to x minus mu over sigma. Our mean is 100, and our standard deviation is still 15. We're still talking about the IQ test here. And we got to solve for x again. And when you solve for x, in this case, you will get an x value of 130.75. Can multiply by 15 and add 100 to both sides. And as an IQ score, that would round to 131. Okay, so an IQ score of 131 will get you, or higher, will get you into Mensa if that's what you're into. All right, so these backwards problems are a little bit more challenging than the other ones, but once you get the hang of them, I don't think they're all that bad. Okay, number 5, the manager of C&R Clothiers, a manufacturer of men's dress shirts, has determined that 3% of C&R's shirts do not meet company standards and are sold as seconds to discount and outlet stores. What is the probability that in a production run of 200 shirts, fewer than 10 will be classified as seconds? So we have a random variable here, x, which is the number of, I guess, seconds in a run of 200. And it is a binomial random variable. We're looking at a fixed number of trials here. They're the shirts. Fixed number of trials. There's 200 shirts. For each trial, for each shirt, either it's good or it's bad. Actually, here we're looking for the bad shirts. And so our probability that a shirt is bad is 3%. And the probability that the shirt is good is 0.97%. So we got a fixed number of trials. There's 2 outcomes for each trial. The probabilities are always the same. The probability that the 198th shirt is bad is independent from whether or not any of the previous shirts were bad. So this is a binomial random variable. And the problem here is asking what's the probability that our binomial random variable, the number of bad shirts, would be less than 10, fewer than 10. All right, now if we were going to do this problem the normal way, we would need to find the probability that there were 0 bad shirts plus the probability that there was 1 bad shirt plus yada 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 all the way up to the probability that there were 10 bad shirts. So there'd be 11, our partition here of this event, there'd be 11 cases, and the complement event has even more. The complement event would go from all the way, oops, sorry, we don't want to include 10, we want to just go up to 9. We just want to go up to 9, sorry about that. We want strictly less than 10, so we want to just go up to 9. So our event here has 10 cases, and the complement event has like 191 cases. So we definitely don't want to work with the complement. And considering that each of these probabilities, we'd have to use the binomial formula, the n choose x times p to the x times q to the n minus x. That's definitely not something that I want to do on my calculator. So this is where we can think about doing the normal approximation to the binomial distribution. If the problem didn't tell us, I think your homework problems specifically tell you to use that. But the fact that we don't want to do this problem would be our clue otherwise. So in order to set that up, the way that we did in class, this is a strict inequality. The one that we were given is a strict inequality. We like to work with an inclusive inequality. X is less than or equal to 9. That would be the corresponding inclusive equality. We should also check that we can use this normal approximation. Remember, that involves checking n times p and n times q. And you really only have to check for the smaller of the two probabilities. In this case, that's p. If we do n times p, that'd be 200 times 0.03. That'll give you 6, which is bigger than 5. So it's just bigger than 5. So we just eked out. This is just barely going to work for us as a decent approximation. So now that we verified that we can do that, our second step here is to introduce a normal random variable, y. So y is going to be a normal random variable. The mean for this normal random variable is going to be n times p. It's going to be our binomial mean, n times p, which is 6. We've already found that value. And the standard deviation for this normal random variable that we're introducing is the same as the standard deviation for the binomial random variable that we're working with, which for binomial random variable, the standard deviation is given by the square root of npq. So in this case, that would be the square root of 200 times 0.03 times 0.97. And when we round this standard deviation to, I guess we'll go ahead and go to 3 decimal places, that would be about 2.412. Remember, you want to give that standard deviation a few decimal places, at least 3 or 4. Okay, so there's our normal random variable that we need to introduce, and this approximation says that, well, this probability about x is approximately the same as a probability about y. This is where we need to do this adjustment. And the best way I have for thinking about the adjustment is for our normal random variable, we're looking at everything. We want to look at everything that's, less than or equal to 9. And when you do the little wiggle, when you do the adjustment for the normal random variable, you need to adjust away. Okay, so we need to add a half to this. All right, so there's, I think, the challenging work in this problem, getting those first few steps done. And then the rest is things that we've been doing on earlier problems. We have a normal random variable. We are asking for a less than probability about that normal random variable. We need to standardize it by finding a z-score. So z here would be our 9.5 minus the mean of 6 divided by the standard deviation, 2.412. We round that to a couple decimal places. That gives us a z-score of 1.45. So when we standardize, I guess this is the point where I guess you can get very, very bogged down in the fact that this is a long problem, or you can recognize that we're basically done with this problem, and now we're just doing this problem. We have a normal random variable. We know its mean and its standard deviation, and we're just trying to find a probability about that normal random variable. We're just doing the same things that we've been doing in all the other problems. All right, so we've got the probability here that a standard normal random variable takes on a value less than 1.45. And when you look, we got a less than problem about z. When you look that value up on the z table, it will be 0.9265. Okay, let's look at one more here. And number 6, Jorge sells magazine subscriptions over the phone. He estimates that the probability of his making a sale with each attempt is 0.12. What is the probability of Jorge making more than 10 sales if he makes 80 calls? So here we have a random variable x, which is number of sales, the number of sales that Jorge makes. And it is a binomial random variable. There's a fixed number of trials. Jorge's making 80 calls. So the number of trials is 80. For each call, the success state here, I guess we're counting sales. So the success is a sale and the failure is no sale. And the probabilities are always the same. Probability of a sale is 0.12. And the probability of not making a sale would be 0.88. And they're independent. The probability of making a sale to Amy is different, or I guess is the same as the probability of making a sale to Becky, no matter whether or not he sells to Amy or Becky. Those things are independent, and so we got ourselves a binomial random variable. And the question here is asking to find the probability that the number of sales is more than 10. Now that partition, if we're trying to treat this like we normally would as a straight up problem, there would be 70 cases for that partition and 11 for its complement. So either way, we're not too excited about doing the partition, and so there's where we would think of doing this normal approximation. If we check here to make sure that we can do it, if we look at n times p or n times q, we should check that both of those are bigger than 5, but you only have to check for the smaller probability. So we're looking at 80 times 0.12, and that's 9.6, which is bigger than 5, so that works out. So we can do our normal approximation to the binomial distribution here. Before we set that up, we want to go ahead and write this as an inclusive inequality. Right now we have a strict inequality, so this would be the probability that x is greater than or equal to 11. That's the corresponding inclusive inequality. And then we want to go ahead and introduce our normal random variable here, y. So y is going to be a normal random variable. Its mean is going to be n times p, going to be the same as the mean for our binomial random variable x, and its standard deviation is the square root of npq. So the square root of 80 times 0.12 times 0.88. And that standard deviation here, go ahead and round this one to 4 decimal places, 2.9065. Again, just playing it safe. No need to be lazy and risk coming up with the wrong z-score here in a couple steps. All right then, and so now that we've introduced this normal random variable, we can go ahead and do the approximation. This would be the probability that this normal random variable y takes on a value greater than. Now here's where we got to do the adjustment. We're looking at 11. We're looking at for everything that's greater than or equal to 11, and we always adjust away from that. So we're looking at 10.5. We subtract 0.5 there. Okay, and now we're done with that normal approximation to the binomial distribution part of the problem, and now we're just answering a straightforward question about a normal random variable whose mean we know and whose standard deviation we know. We're going to go ahead and standardize that normal random variable with a z-score. The z-score is going to be 10.5 minus the mean of 9.6 divided by the standard deviation of 2.9065. So here again we're using our formula. Will normally be x minus mu over sigma, but now we're doing y minus mu over sigma, since our normal random variable here is y. So we're just using that z-score formula, and that'll give us a z-score of about 0.31. So now we're looking at the probability that a standard normal random variable takes on a value greater than 0.31. So now we have a greater than problem about z. There's a couple of strategies. Using the complement strategy, you would get that this is 1 minus the probability that z is less than, I guess technically less than or equal to 0.31. That would be the complement. The or equal doesn't matter here for normal random variables. So that would be the complement strategy, and you could look up this probability on your table and subtract it from 1, or if you're using symmetry, this would be the probability that z is less than negative 0.31. We can take our probability here and flip the inequality, and also flip the sign on the z-score. I'm really starting to like that strategy over the complement strategy. Regardless of which strategy you employ for the greater than problem, you should end up with a final probability of 0.3783. All right, so that'll do it for the exercises here. I did want to take the opportunity I think I want to go back to this problem and look at how this is an approximation. We can use Excel. Excel's pretty decent. I'm going to crack open an Excel spreadsheet here so we can look at, here we go, how you might get the job done in Excel. So if you're content with what you've seen so far, you can go ahead and feel free to stop the video now. But if you want just a little bit more insight into what we're doing here with this normal approximation, and we can investigate how good of an approximation it is, go ahead and keep on watching. This won't take too long at all. So the idea here in this problem number 5, we're looking at, we got a bunch of x values, and we're going to find their corresponding probabilities and then add them up. And so we've got x's between 0 and 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the corresponding probability, we're going to use our binomial formula for each of these. So if you never used Excel before, this might look a little bit wonky. But we're doing, let's see, the name that Excel gives for the combination, the choose, is just combination, or combin. Combin, we have how many? We have 200 trials, and we want to use this value for x, and we multiply p times p to the x. That would be, in this case, 0.03 to the x. That would be that cell right here, times q, 0.97 to the n, which is 200, minus x. Okay, so there would be that first probability, and then Excel's really sweet, allows you to drag that formula down. and then add things up. Where's I don't have my sum button. All right, equal to sum. All right, then we can add those up pretty quickly in Excel as well. And Excel gives us 0.9192. Was that our probability here? All right, that wasn't exactly our probability. So the true value for this problem, even if we round to the nearest, if we round to 2 decimal places, they still don't equal. So now remember, we just barely met the threshold. We just barely met the threshold for this guy. N times P was just a little bit bigger than 5. So we just barely met the threshold for this one. Also, the approximations get a little bit worse when you go to the edges. So when we're working with in-between probabilities, this approximation does a pretty decent job. But if you start to incorporate anything at the ends, then the approximation starts to get a little bit wonky. And so we can see here that the approximation isn't perfect. This is the actual true value of this probability, and this is really just an approximation. Okay, that'll do it for this video. If you have any questions about anything from the video, please make sure you ask, and we'll see you in the next one.